Chemical formulas contain a lot of information that's very useful. They give us relative quantities of each element in a compound, and that can be expressed in different ways. One way is mass percent composition, or sometimes just called mass percent for short. And this is the percentage of mass that is a single element out of the whole compound's mass. And so this is the general form for percentages, which I find useful because I can really figure out almost any percentage problem if I just remember this. Percent is the part over the whole times 100. So here the part is the mass of the element we're interested in, and the whole is the mass of the whole thing. We can get this information from the formula of a compound or from experimental mass analysis. In an experimental mass analysis, and we'll do one of those in lab, you find out you have so many grams of this element in so many grams of the whole compound, and you just literally divide those numbers. Percentages require a little more calculating. A percentage does not change based on the sample size. So it's always going to be the same percentage. It doesn't matter what size the sample is. So that means that we can choose the sample size if it's not given in the problem. And so we might as well choose it to make it easy on ourselves. So we're just going to choose to talk about 1 mole of a compound because then it's very easy to calculate the masses. So here, acetic acid is the active ingredient in vinegar. Calculate the mass percent composition of oxygen in acetic acid. So percent oxygen then is going to equal the mass of oxygen divided by the mass of the acid. And then multiply by 100. If we look at this formula, it starts with H, right? And it has oxygen in it. It looks a little weird because there's so many letters here, but you cover up the H, and what's the name of that oxyanion? Acetate. And we change ate to ic and add the word acid, and we get acetic acid. So we're given the formula there, and we are just going to choose the sample size. We're going to choose 1 mole of it, just because it's easy. You can do something else if you want, but it's harder. So what's the mass of 1 mole of acetic acid? The molar mass, right? So we got to calculate that. How many hydrogens in the formula? 4. If you want to treat them separately, that's fine, but there's 4 hydrogens. And 2 carbons. And 2 oxygens. (60.052 grams is the mass of 1 mole. So here, grams of acetic acid, that's this part down here, the mass of 1 mole. So we can plug that in, 60.052 grams. And then we need to know what's the mass of oxygen in that amount of acetic acid. We wrote out the calculation, and so it's actually sitting right there. It's this thing right here. That is the grams of oxygen in 1 mole. So you could multiply that out and write 32 in the numerator, or you could just write it like that, 2 times 16. grams times 100. Now this one is going to give us a bunch of digits. 53.2871, and it just keeps going. How many significant figures should we use? Well, I kept track of them in here for us. So what do we have up here? 4 and 4. And this 2 is exact. Just like the number of children. There's 2 or 3. Can't have 2.3 children, right? So that's exact. So this should have 4 sig figs. Stop it right there. 53.29% oxygen. Any questions? If we know the mass percent composition, we can use that as a conversion factor and go between mass of an element and mass of the compound. Percent literally means per 100. So if Freon 112, which has this chemical formula, is 69.58% chlorine by mass, that means we've got 69.58 grams of that element, chlorine, for every 100 grams of the compound. So that's a great conversion factor between mass of Freon and mass of chlorine. So here's one where they give us the mass percent. What mass in grams of iron 3 oxide contains 58.7 grams of iron? Iron 3 oxide is 69.94% iron by mass. Well, let's identify what they gave us. 58.7 grams of iron and 69.94% iron. And what are we trying to find? Yeah, mass in grams of iron 3 oxide. So we've got 2 numbers given to us. Let's write them both down. Percent is per 100. So let's write it that way. Grams per 100 grams. Grams of what? So grams of iron, right? Grams of iron per grams of compound. Now, writing out iron 3 oxide is kind of long, so I'm going to write its chemical formula. And this 58.7 grams is grams of what? Of iron. So this is a problem where we have masses of 2 different things, and so we can't just use grams, we need to specify mass of what. So then I'm trying to find grams of iron 3 oxide. Our starting number is going to be this original mass, because there's no way that's a conversion factor, and this actually is a great conversion factor. So we can go directly from grams of iron to grams of the compound using this mass percent. 58.7 grams of iron. Do this in one step. Go to grams of Fe2O3, and we'll divide by grams of iron. Our conversion factor is here. How many grams of iron? 69.94. How many grams of the compound? 100. And when we're dealing with a percent like this, the uncertainty is indicated in this number, and that so it's per exactly 100 grams. So 58.7 times 100 divided by 69.94 equals, how many sig figs should this answer have? 3. because our starting mass only had 30. Oops, that's not percent. Grams. Well, you write the units down. Grams of iron 3 oxide. Any questions? We can also get conversion factors from chemical formulas because the formulas give us the relationship between numbers of particles. How many atoms of this thing are there for how many atoms of the other thing, or molecules. So this Freon, again, we could get several different conversion factors out of this. One of them would be 2 moles of carbon for every 1 mole of compound. Because in one formula unit, or one molecule, there are 2 carbon molecules, right? 2 carbon atoms. 2 carbon atoms per molecule of Freon. And then if we multiply by Avogadro's number, we get moles. And so we get 2 moles of carbon for every mole of compound. We could also look at the chlorine. There's 4 chlorines in the formula, so it's 4 moles of chlorine per mole of Freon. These are masses in they're not masses. These are relationships in moles, not masses in grams from the formula. Determine the mass of oxygen in a 7.2 gram sample of Al2SO43, aluminum sulfate. Again, let's treat this like dimensional analysis, starting with 7.2 grams of this guy. And what are they asking me for? Mass of oxygen. Okay, so I need to figure out how I'm going to get from one place to the other. So I've got that many grams of the compound, and I'm trying to figure out how many grams of oxygen. Well, what probably goes in the middle? Moles. Moles in the middle. I can convert grams of aluminum sulfate to moles of aluminum sulfate. Yeah, and then from the formula, I can tell how many moles of oxygen are in that many moles of the compound. And then I can get to grams of oxygen. The mass percent was easier. This one's more chemistry. Chemists really like moles. I should bring my moles to class someday. I have 2 stuffed moles in my office. Not taxidermy moles. Stuffed animal moles. Wearing lab coats. They're very cute. So I wrote out the path. I'm just going to copy that down. So moles of aluminum sulfate. And I agree with you. It's very tedious writing out that formula. Moles of oxygen, grams of oxygen, but it just has to be done. So down here we have grams of Al2, SO4, 3, and here we have moles of Al2, SO4, 3, and down here, thankfully, is just moles of oxygen. And our units are canceling out the way we